My name is Seth Eddington from the University of Illinois at Springfield. This is my spectral analysis of C13H9NO3. To begin the spectral analysis, we will start with mass spectrometry. We will look for the M+ peak, which usually is the farthest right peak that we see. It also is the sum of all the molar masses of the atoms that we were studying in the molecule, which this is 227 here. So our M+ peak is 227. And then we were going to look for our base peak, which is the largest peak in the graph. So that also happens to be 227. So our base peak, 227 as well. Now to calculate the DOU. This is the formula for the degrees of unsaturation, which is 2 times the number of carbons, plus 2, plus number of nitrogens, minus number of halogens, minus number of hydrogens, all over 2. So for this molecule, ours will be 2 times 13, plus 2, plus 1, minus 0, minus 9, all over 2. In total, our DOU equals 9. This is important because in total we will either have 9 pi bonds or rings in our molecule. Now we're going to look at possible fragmentation patterns. So we're going to take our M+ peak minus a couple of the other larger peaks that we see, such as 150 and 105. So we take 227 minus 150, which gives us an M- of 77. And then if we take 227 minus 105, we get M- of 122. Now, it is important to note that an M- of 77 usually means that there is an aromatic present in our molecule, and it is also noted here by this peak here at 77. Now, also what we can do here is we know that down here we have 76, so it's minus 1, which means we have 1 hydrogen off of the aromatic. And lastly, we have no halogens. Now we can move on to the next chart. The next chart that we're going to be looking at is infrared spectroscopy, and this is a chart to show different functional groups and things going on in the molecule. It's something good to look back over when we're examining our next chart. So for infrared spectroscopy, we need to start by identifying the 5 different zones. So I've laid them out here, and we start off with zone 1 here. That goes from about 3700 to 3200. Zone 2 is 3200 to 2700. Zone 3 is 2300 to 2000. Zone 4 is 18 to 1600. And Zone 5 is 1600 to 1400. Usually the rest of the graph is considered the fingerprint region, and we do not pay much attention to this, but we do have an exception here, and we'll get to that in just a moment. So for the first zone, we see that we have no significant peaks or anything like that from 3700 to 3200. This is where we would normally find alcohols, carboxylic acids, things like that. But we do not have anything here, so I'm going to write none. Now we're going to look at zone 2. This is where we're going to find carbon-to-carbon double bonds, or sp2 bonds. And we see that we do have a peak here at 3101, so we're going to write sp2 carbon-to-carbon double bonds there. That should show up in our molecule. Zone 3, we'll see nitrile groups and alkynes, but we have no significant divots there, so none. And in Zone 4, we see we do have one at 1651. This is indicative of carbonyl groups, so carbon to oxygen double bonds. So we probably have that in our molecule. Lastly, Zone 5, we see that we have a pretty significant dip at 1512, and this could possibly be due to a nitrogen to oxygen bond, but we're not 100% sure on that. Lastly, I know that we had said that we usually ignore the fingerprint region, but this 700 over here can also indicate nitrogen to oxygen bonds as well. Also, this line here, the start of the graph, is very, very low compared to normal. Usually it would be above 30 or so. Now, this is an indication of aromatic rings, and the symmetry will also do this too. So we know that our molecule more than likely has some symmetry, and it's probable that we have rings in there, which we also found out from our mass spec earlier. This is a chemical shift guide for proton NMR, which we will be doing next. Now we are going to look at proton NMR. So over here on the left, we have our whole chart for NMR, and on the right here is an exploded view of this right here, just so we can see the splitting patterns between the hydrogens. So we ignore this one large peak. It is not part of our splitting or anything like that. So we notice that we have 1, 2, 3, 4, 5 groups for hydrogen, so that means we're going to have 5 different environments total. That will help us later on. Now, the 2s and the 1 here are our integration number, telling us how many hydrogens are in each of the environments that we're going to find. So now, we're going to go ahead and attempt to draw the structure of what we believe the molecule looks like. So we know that we have rings, we know we have carbonyl groups, we know we have nitrogen, oxygen bonds, and we have relative symmetry. So we'll start with drawing our rings. So now we've used up 12 carbons, we have 2 rings, and we have alkenes, trienes. So now let's try and find our carbon, our 13th carbon. So that gives us good symmetry here. We've used up all of our carbons, and we will go ahead and use one of the oxygens, which satisfies our carbonyl group as well. And lastly, remember the nitrogen-oxygen bonds that we possibly had. We do need to throw that in there since we do have a nitrogen. So we're going to just go ahead and put it here. Nitrogen is used. We have an oxygen and an oxygen coming off, which is a nitro group, but we usually have a double bond to one of the oxygens. So now we're going to see if it satisfies our DOU of 9. We have 1, 2, 3, 4, 5, 6, 7, 8 double bonds, and we have our rings. So this does satisfy that. And now what we need to do is make sure that we have the correct number of hydrogens. So we have 1 hydrogen here, 1 here, 2, 3, 4, 5, 6, 7, 8, 9. And we have no more hydrogens over here, none over here. We do have 9. We used up our 3 oxygens, carbons, and nitrogen, so we have actually gotten the molecule as correct as we can. Now we are going to attempt to find the different environments. So that will be shown here with the green highlighter. We know we need 5 environments, and we know where all of our hydrogens are. So we're going to start and say that our 1 here is going to be right here. That is our 1 group. This can be our 2nd group, this carbon and this carbon right here. And then our 3rd group, which is here, goes to this carbon here. So we will go ahead and mark those in. And I will actually do it down here in the exploded view to make it a little bit more simple. There. And then this, the 2nd group, is going to be another one that's very far down or upfield, because the hydrogens closest to the most electronegative atoms will be the farthest left on the chart. This is due to downfield shift. And now our 3rd one will be a little bit farther upfield, and that will go right there. Now moving on, we still have 2 more environments to do, and it's going to be this guy and then down here. Those 2 are connected in one environment, and then our last 2 here and here is our 5th environment. We'll go ahead and put those into the chart here. Notice this group is going to be for this peak, because it is not quite as close as the last one is, which will be the farthest downfield, next to the nitro group. So we can also see that we have splitting patterns here. We have a doublet, 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 triplet, and triplet. That results from the n+1 rule around the hydrogens. So for example, this hydrogen here with the 1 integration number, it has 1 hydrogen to the left of it, 1 hydrogen to the right of it. So we do n+1, which is 2, 1, 2, plus 1, 3. That's why we get a splitting pattern of 3. All of these do work with each of the splitting patterns, so we do know that we in fact have the correct structure. This is a chemical shift guide for carbon-13 NMR. So for carbon-13 NMR, we're going to figure out where the carbons fall on these charts. So on the left we have the regular chart as a whole, and then on the right we have the exploded view. I have numbered each of the peaks that we need to pay attention to, and it comes out to a total of 9, which we can see down here. So what we're going to do is we're going to just figure out which carbon corresponds to which peak. The farther left on the chart, the closer the carbon is to an electronegative atom, just like in proton NMR. So for number 1, it will be the closest to an electronegative atom, which would be this guy right here. Number 1, it's double bonded to the most electronegative atom in the molecule. So the next would be 2 right here, because it's closer to the nitro group and the double bond oxygen, and then 3. So from here we're going to actually move down towards the nitrogen, because that is our next most electronegative atom, and it's as close as it possibly can get. And from here we're going to start off with groups, because we know that we have more than just 9 carbon atoms in our molecule. We have 13, so multiple carbons are going to be in the same group. So from here we have 5 and 5, 6 and 6. See how we're moving away from the electronegative atoms. 7, 7, 8 and 8, and our last group and last carbon is a single, and it is 9. So thank you so much for watching the video, and that is how you use spectral analysis to figure out a structure and molecule. Thank you.